Hey class, I just wanted to make a quick video over each of these simple machine slides, just because I want to point out some of the points that I think are important. So let's take a look. It just goes over, we're going to go over the lever, wheel, and axle pulley in this one. But there are six, so the other incline plane, wedge, and screw are in the other um, PowerPoint. The main thing to understand about some machines is that they create a mechanical advantage. Okay, so and the mechanical advantage is shown in a ratio. And a ratio is just a relationship between two different things. So the ratio of magnitude, the ratio of distance. So the magnitude will be forces. The distance traveled by the force is also going to be a mechanical advantage. And we're going to talk about the difference between those two things. So let's look at this example that they give with this inclined plane here. It has a mechanical advantage of 4-to-1. Tells us what about a mechanism. So when it says 4-to-1, what does that mean? Well, the yellow box here, for example, ultimately the goal is to get the box up to the top of this ramp or that distance, whatever that distance may be. So in this case, let's say that distance is 3 feet. We have to move this heavy box up here. Well, this is 3 feet, and the ramp right there is 12 feet. So, okay, so that means it's 4-to-1 mechanical advantage. Why though? Well, we can look at it two ways. Say this box weighs 400 pounds. Theoretically, we would only have to apply 100 pounds of force against the box to move it up 3 feet using the ramp. If we weren't using the ramp, we'd have to lift 400 pounds, right? So, and that's not perfect because that's actual mechanical advantage. But if we're just dealing with the distance and we say 3 and 12, okay, we take the distance of the effort divided by the distance of the resistance, which is the 3 feet. 12 divided by 3 is 4-to-1. Same thing with the weight for actual mechanical advantage. And the only problem with actual mechanical advantage is if this was a 400-pound box and I did apply 100 pounds there of force, it probably wouldn't move the box because that would be ideally it would move the box. That's the minimum amount of force I could use to move the box. But we know that we live in a world of friction, so actual mechanical advantage is going to be a little bit different. So we measure the actual force it would take to push that box up. So say if it's like, I actually had to apply 120 pounds of force to move the box, then our mechanical advantage is going to be a little less than 4-to-1, which is always the case. Actual mechanical advantage is a little bit less than ideal mechanical advantage. Okay, this slide talks about work. So work is what? Work is the force applied on an object times the distance the object travels parallel to the force. So work in the sense that they're talking about here is the formula for it is force times the distance parallel. That's important. That those little signs say parallel. Force times the distance perpendicular is something else, which we'll get into. But force times the parallel distance is work. So if I'm moving a refrigerator, I think maybe there's an example of a refrigerator being moved. If I'm pushing a refrigerator and it's a 200-pound refrigerator, or I'm pushing 200 pounds and I'm pushing it for 30 feet, it's the amount of work I've done is 200 times 30. And it would be pounds force pounds. All right, so work, the product of the effort times the distance traveled by the same regardless of the system of mechanical advantage. We talk about this one is the magic number, mechanical advantage. So mechanical advantage, if a mechanical advantage is greater than 1, what does that mean? That means that, hey, it's greater than 1, that means my force is increased. So if I apply this much force, the output force is going to be more. If it's less than 1, it's the opposite. So I apply this much force, my output force is a little less. It talks about 0. Mechanical advantage can never be less than or equal to 0. Why do you think that is? Well, think about that. If we have a greater than or less than, it can't be less than or equal to 0. We apply a force, it has to go somewhere. All right, so here we go. Ideal mechanical advantage. Ideal mechanical advantage, DE, distance effort over distance resistance. Going back to that inclined plane, the distance that I had to travel up, let's just say the 3 feet versus the distance of the ramp. I'm sorry, the distance that I travel up was the effort distance, so that would be 12 feet. The distance of the ramp would be the 3 feet, or the distance of resistance would be 3 feet. So that would be ideal mechanical advantage deals with distance, right? Well, the actual mechanical advantage deals with the force. So when we had to push that box, 100 pounds of force couldn't necessarily move that box because we knew that there's friction involved. So it would have been maybe 120 pounds. We said, okay. So now we have the force resistance 400 divided by 120. Hey, that's no longer a 4-to-1 mechanical advantage. The actual mechanical advantage is a little less than 4-to-1. Okay, then they give some real world mechanical advantage examples. Can you think of a machine that has a mechanical advantage greater than 1? Okay, it's like anything that is the machine is used for. But what about a machine that's less than 1? Think about workout things. They're meant to give us resistance. That's why with resistance, it can help us get stronger, right? So there's the machines in the workout room that takes more effort than the output. So you think about like something with a pulley on it to make it harder to pull up. Kind of interesting. All right, so going into levers here, we're talking about 3 different classes of lever. We got first class, second class, third class lever. And it's really just the relationship between those 3 things. The things that I'm talking about are, I'll move it over to the light. Resistance, fulcrum, and the effort. So if we're looking at your screen and you see the top lever here, that's a first class lever. Why? The fulcrum is in the middle. Okay, so I like to think about it like, where's the fulcrum located, and what's in the middle is what I like to think about. So if the middle thing is a fulcrum, it's going to be the first class lever. If we look at a second class lever, what's in between there? Well, the resistance is there. So for a second class lever, the classic example is a wheelbarrow. The wheel's out in front, that's the fulcrum on a wheelbarrow. The load is in the middle, and I'm lifting the wheelbarrow up like this. Move on the screen. And I'm the effort. So I'm pulling up, the load's in the middle, and the wheel is the fulcrum. So when the load is in the middle, that's a second class lever. And lastly, the third class lever, the effort's in the middle. Well, what are these for? Well, a third class lever is never going to give you a positive mechanical advantage. What do you mean by that? Well, a third class lever is not designed to make your work easier. A third class lever has some other function to it. So if we think of tweezers, for example, tweezers are a lever. Okay, the fulcrum is where the tweezers are attached. And when I press my fingers together, that I'm in the middle, and whatever I'm grabbing on the end of the tweezers is the resistance. Well, a tweezer's purpose, like say if I'm picking out one of my nose hairs with a tweezer, right? I'm not like, man, I don't have enough force to grab this nose hair. It's not necessarily the case. It's just that I need to get a better grip on it. It's actually decreasing my force slightly, but there's a different reason for the third class lever. So let's explain the math behind that though. Let's look at the math behind that. Whoa, whoa! First class lever, if we look at it, it could be either greater than or less than 1, depending on the distance factor. So just like before when we looked at the ideal mechanical advantage, let's talk about the distance effort over the distance resistance. So if my distance effort has if there's a greater distance from where I'm pushing down to the fulcrum, my output's going to be greater. This one's equal to 1, say, because it's the same distance right here. But it makes sense, right? I remember, you guys remember Bill Nye? Bill Nye, the science guy? There was one that he did on levers, and he was pushing down on this lever, and it was a really big lever, and like it was just a classic teeter-totter thing. He's pushing down on it, and he lifted this whole band that was like playing music, like, it's the 80s, so they were playing music, and it was just him, and he was on one side, but the effort arm was really long. So he amplified his force by quite a bit. So if we think about that down here, the mechanical advantage is greater than 1 with the effort arm increased, dE. Let's look at that mathematically. So if I have my lever here, and I have my fulcrum in the middle, or not, let's say it's not in the middle, let's move it to right here. I have my load of classic 100 pounds here, and I have my resistance that's farther away. This is a farther distance right here. Well, if this was 2 feet, this distance here was 2 feet from the resistance to the fulcrum, that would be the distance resistance, dr, d sub r. The distance effort would be on top, dE. Numerator, denominator. Say if the effort arm was 6 feet. The ideal mechanical advantage doesn't matter what the force is here for the load or for the resistance. You only need the distances. So 2 feet, 2, 6. So 6 divided by 2, 6 being the distance of the effort arm, and 2 being the distance of the resistance arm, is 3, right? That's going to equal 3, I think, right? 6 divided by 2? Yeah, 3. So 3 is the mechanical advantage in this situation here with 100 pounds of force on the end. So how much force would I ideally need to apply to lift up that 100 pounds? $33.333334. So just over 33.333 repeating force here would lift the 100 pounds ideally. So that's my mechanical advantage of 3. Now, with the friction of this system, it's probably going to be more than 33 pounds to lift up that 100 pounds, but that's actual. So I'm going to skip these because they're talking about the different classes of lever. We already went over that. But let's look at moment. What the heck is a moment? Very simple. It's a moment in time. No, it has nothing to do with time. Okay, this moment has something to do with torque, or the distance times the force. But what kind of force? Or what kind of distance? The perpendicular distance. Remember how I said that's something else? So when I have a wrench in my hands and I'm using it to turn a bolt, a rusted old bolt, the longer the wrench, the greater my force is going to be. Why? Because it's distance times the force, and I'm pushing down on the wrench. The wrench is like this. Say it's like this on the wrench handle, and I'm pushing down on my hand here, see that's perpendicular. My force is down. The wrench is this way. That's perpendicular, right? Hopefully you understand that. All right, we can look at this. So calculating a moment. And this is why it has to do with the lever. So the reason why we're starting to talk about moments now is because moments have to do with force. So we just looked at a couple slides that dealt with the distance of the effort arm, the distance of the resistant arm. That was talking about ideal mechanical advantage. That's all about the distance here. But now we're starting to talk about force. And why are we talking about force? Because we're starting to talk about actual mechanical advantage. So we're starting to bring up force here. So I shouldn't have moved my camera because I want to move it back now. That doesn't matter. We'll use the example on the screen. So if we have 15 pounds of effort force and there's 5.5 inches to the fulcrum, we have a new kind of force here. Our force is a little different, right? What? What do you mean? Well, our force now is 82.5 inch-pounds. Wow, that's more than 15. Yeah, it's quite a bit more. But the resistance has a moment related to it as well. So let's take a look. Okay, so this is talking about lever moments. So when the sum of all the moments on a lever equals 0, the lever is in rotational equilibrium. This is not talking about mechanical advantage, right? Because the mechanical advantage can't equal 0. So we're talking about when the forces cancel out each other, meaning the forces on this side of the teeter-totter equal the forces of this side of the teeter-totter. Right? This makes sense. Like playground, classic cartoon playground. Big kid on this side of the teeter-totter, little kid on this side of the teeter-totter, right? If those kids are equal, the forces are no longer moving up or down. They're going to equal to 0, and you're at rotational equilibrium. It's not moving counterclockwise or clockwise. Okay, now we're doing up on the screen, looks like we're doing a lever moment calculation. So we have the 82.5 pounds of effort. Well, it's saying, okay, well, using what you know regarding rotational equilibrium, calculate the unknown distance from the fulcrum to the resistant force. So it gives you like an example of, okay, well, what if this was 36? What if on this side that we had 36.66 pounds, or 36 and 2/3 pounds on this side? Well, what would the distance of the resistant arm have to be for it to equal, or for it to be rotational equilibrium? We'll have to equal that side. 82.5 on one side of the equation would have to equal 82.5 on the other side of the equation. So it's just basic algebra at that point, because we have 82.5 and we have 36.66 times x, or in this case, x is the distant resistance. That has to equal 82.5 over here. So 36.66 times 2.25 equals 82.5. And you do that by what? Well, we have 82.5. We divide 36, but divided by 36.66. That leaves us with the x on one side of the equation, which is 2.25. Okay, that's right here on the screen. So then we know, okay, the distance of the resistant arm is 2.25 inches. Ha-ha! Okay, now it's going into other things. We're talking about lever, but this is kind of moving into, well, this is not. This is kind of something we already talked about, but we're moving a little bit into wheel and axle. So wheel and axle is not too different from the lever. So now we have ideal mechanical advantage, which is the distance effort over the distant resistance. You may know that. You can see that there. You can kind of see it right here where it's talking about circumference. So 2 pi and 2 pi, resistant arm, resistant effort arm, resistant arm. Ideal mechanical advantage is the effort arm over the resistant arm length. I was talking about that from the beginning, so this slide's a little bit irrelevant if you've been paying attention. Okay, but then we have a lever, AMA. We just covered that too. It has to deal with the forces. So the force resistance over the force effort is going to equal AMA. So it switches. If you notice, the effort and the resistance switch between IMA and AMA. The IMA, ideal mechanical advantage, the distance effort's on top divided by the distance resistance on the bottom. And on actual mechanical advantage, the force resistance on top divided by the force effort on the bottom. Okay? The next thing that we want to talk about, especially when it comes to mechanical advantage, is efficiency. Okay? So actual mechanical advantage, ideal mechanical advantage. If the actual mechanical advantage equaled the ideal mechanical advantage, that would be 100% efficient. You're like, this mechanism is 100% efficient, which is impossible. But that's what it's showing, the relationship between the ideal mechanical advantage and the actual mechanical advantage. Well, what's the formula? What's right here up on the screen? The actual mechanical advantage divided by the ideal mechanical advantage times 100. It's just like a grade, right? I give a test out and it's worth 50 points. You get a 46 on it. Ideally, you'd get, a 50 on it and you get 100%. Well, you get a 46 on it. 46. Ideally, it's 50. You'd get a 50, but actually, you got a 46. What's your percentage? What's your grade? So that's the same thing as what you're doing here for efficiency. You just have to remember that the actual thing that happened, AMA, is above the ideal thing that could have happened, IMA. So then you multiply by 100 to get the percentage. Okay? So in that case, we look at something where, hey, we did an equation with the distances, and we came up with the ideal mechanical advantage of 2.44 here. Well, then when we took the forces, though, so maybe this was a lever, and we said, okay, with the distances, it's 2.44. Well, with our forces, with the resistance on this side and the effort on this side, when we measured the effort, it actually was more like this. It was more like a 2. And you say, okay, well, 2 divided by 2.44 times 100, that's 82%. Well, that's an 82% efficient machine. That's pretty much the loss with the friction, okay? And that's it. I'm going to stop this video, and we'll continue with the, what's it called? The wheel and axle after this. So this is just going to be the mechanical advantage and lever video. All right, adios.